Alright, hello MEGN 300. Today we're going to be starting off on a new unit where we're going to be talking about frequency analysis and how we can look at signals that are changing in time and analyze those signals and gain useful information based off of how those signals change with respect to time. So here's why we're doing this. So far in the class, when we've been working on your scale project, we assumed that your signal was not changing in time. So a good example is your scale project. In your scale project, the weights are all pieces of metal that are just sitting on the end of your scale. They don't change unless you physically move them out. There's no significant change in that signal with respect to time. But for a lot of engineering systems, that's not true. And in fact, we want to see signals that are changing in time because we can get useful information out of them. Good example of this would be analyzing vibrations. So we have a picture here of a bearing that's failed rather catastrophically. When bearings are starting to go out, they vibrate in different ways than a healthy bearing does. So we can take that information, we can analyze vibrations coming out of machinery and start to see if different bearings or different items on that system are starting to fail. For things like microphones, right? Microphones are picking up sound, which is a pressure signal in the air that's varying with respect to time, and that's what our ears interpret as sound. So being able to design a good microphone to capture the frequencies that we want to get a good sound without capturing some of the frequencies that would lead to undesirable sounds is really important. That's actually what that funny shield is to the side of the microphone in this picture is called a pop shield. So when we're talking, we make sounds like a P sound. A lot of times those really harsh sounds will sound like a pop on the microphone, so we can build like a physical filter element to not allow those frequencies to the microphone, or at least soften, taking the edge off of them, which makes the videos like this one nicer to listen to with headphones on. And then also for systems like optical systems, right? So light has lots of different frequency components based into it. So red light is at a lower frequency than blue light is, which you can see if you have a prism and you're breaking the light apart. We can use this frequency information of the light to do all sorts of different experiments. That's what the whole field of spectroscopy is based off of. All right. So the key idea here is we're generally looking at the frequency of these dynamic signals. So the question is, how many cycles per second or hertz does the signal complete, right? So that's sort of the key quantity that we'll be looking at in this upcoming unit here. So we'll talk about how we can determine what those signal frequencies are, and if we have a complex signal that's actually got a bunch of frequencies mixed together, how do we break those apart and analyze them? So we'll be talking about the Fourier transform and how that mathematical operation can help us with this sort of analysis. All right, we'll also be talking about noise. So noise is stuff that we don't want in our signal. So this extra signal that comes in is not related to the phenomenon that we're trying to measure, and it gets in the way of the actual signal that we want to be looking at, right? So these noise variables that can come into our measurements mask what we're actually looking for, and it can increase variation in our measured variable, so it relates to our precision error of our instrument. So we'll talk about how understanding the frequency of our signal and understanding how noise is distributed across frequencies can allow us to design filters so that we can reduce the noise in our instruments and sort of take care of that and be able to measure smaller signals more reliably, right? We'll also be talking about how we determine the sample rate that we collect data at, right? So far we've just told you in lab you should set your sample rate to this to make sure that you get the lab to work. But we'll talk about where do those numbers actually come from, right? So if you are looking at some signal out in the world and you know it's changing in time, how do you determine how quickly you need to take data to be able to reliably capture that signal and make sure that you have an accurate representation of the signal? So we'll talk about aliasing and why that's a bad thing and why we don't want that to happen, how to prevent it from happening. All right, and this is all going to come together in Design Challenge 2. So the premise of Design Challenge 2 is you have to detect a reflected optical signal from as far away as possible. So we'll give you a laser pointer, and you'll be shining that off of a mirror and detecting the reflected signal coming back towards you. right? And the idea here is taken from the NASA Lunar Ranging Facility experiment. So what they do there is the Apollo astronauts, when they went up to the moon, they left behind these arrays of mirrors that are retroreflectors. So if you shine a light at them, the light always goes straight back the direction that it originally came from. So what we have here on Earth is we have a large laser. We zap the moon with the laser and bounce it off those retroreflectors, and we time the amount of time it takes to go, the laser takes to go from the observatory out to the moon and back, and from there you can determine how far away the moon is because the speed of light is known. So the trick with this is you lose the vast majority of the light that you send out in the laser beam originally. So your signal is very, very small. At the same time, any sort of stray light, just ambient light out in the environment is going to be picked up by your detectors that are looking for the laser beam. So that's introducing noise into your measurement. And what we need to be able to do is filter out all of this noise, get rid of the noise so that we can just see the signal. And the better job we do filtering, the more faint of a signal that you can pick up. So for what we'll be doing is you'll be setting up a sort of miniature version of this experiment where we're just going to try and detect that reflected signal from as far away as possible. So the better job you do designing your filtering system, the further away you can move your mirror, and the fainter reflection of the laser beam that you'll be able to see with your detector system. So we'll be putting some extra credit on the line, so whoever can see their reflected signal from as far away as possible, further than anybody else in the class, you're going to get some extra points on that assignment. So that is the motivation where we're heading with this unit. We'll have some more videos up where we'll talk about some of these topics in more depth to help you get through your LabView assignment and your design challenge. So we'll see you in the lab, and we'll be looking forward to a good unit.